Thank you all for coming out today. I've got a variety of things to talk about here. This image that you've been looking at for the last 15, 20 minutes or so is an image of Mount Sharp. It's a mountain in the middle of a big crater. This mountain is about 5 kilometers high, so it's higher than anything in the lower 48 states of the U.S., even higher than Mount Whitney. And down in the shadow that you can see over here is a little rover called Curiosity, and she is about 2 meters high. And the reason that we sent this rover to Mars at the base of this mountain, where she's now exploring, is to try to get an answer to this question that humans have asked for so long, which is, are we alone and where do we come from? So where do we come from part is the study of the early Earth, which, as Nate said, is one of my interests. And the are we alone part, the only way you can ever answer that is to go out and look. And so Mars is our closest neighbor. Turns out it's a planet that actually was very similar to Earth, maybe not a sister, but a close cousin. And by studying the rocks that are in this mountain, we can get clues as to whether or not life could have ever originated on Mars. So that's what we're going to talk about today, mixed in with a few adventures and some other stuff. It takes a big team to operate Curiosity. These are the engineers and scientists that work at JPL every day. These 200 people are required to do something as primitive as uplink a command sequence that says drill a hole in the rock that deep. This is like the pinnacle of humanity, $2.5 billion to drill rocks on Mars. But it takes 200 people and operations staffing at JPL. In addition to that, we have another 450 scientists that are spread all over the world, 13 different countries. Almost every time zone is represented, so we have complex operations for people to dial in by telecom to participate in the science discussion about what we will do. So it's a very diverse and active team. All right, what I want to start first is with a topic about, what most people hear about these missions, and they think that let's go to Mars and find evidence of water. And that's been going on for a couple of decades now. But what we're trying to do is characterize the environmental quality of that water to see if it really supported a microbial record. And by doing that, we make comparisons to the similar questions that we ask on Earth. So I want to talk a little bit about where we are in the history of science and how we're exploring on Mars and how it relates to what we were doing on Earth about 150 years ago. Okay, so let's go back to the late 60s and early 70s. There's an orbiter. Actually, it's a flyby. The first set of explorations to Mars just were a spacecraft that zipped by, took some pictures, made a few other measurements, and then off they went. Viking was the first to actually go into orbit and then eventually put a lander on the ground. So we have these channels that you see from orbit, and anybody that's ever looked at a satellite picture of the Earth, you see river basins with lots of tributary streams coming into it. It's really easy to imagine that there was a fluid flowing across the surface. But in planetary science, you have to ask the question, well, how do we know that fluid was water? Maybe it was liquid carbon dioxide. Maybe it was liquid nitrogen. Something like that could have been flowing across the surface. So it was a big mystery. And then when Viking came along a decade later, it took pictures again, and the problem didn't go away. It just got more highly resolved. So these features were there. The leading hypothesis was on a planet which is now bone dry, there was once water flowing across the surface a long time ago. What happened? That's really the big question that we ask about Mars. Now when you look at this, you can anticipate another question that comes out of it, which is if the water is flowing across the surface and carving channels into bedrock, well, that bedrock has to break down into fragments and be transported away. But it took almost 30 years to be able to find the evidence for that. And here it is. It's a place called Eberswald Crater. And now what you're looking at, instead of a channel that's cutting down into bedrock, you're looking at a channel that represents something like a river delta. So if you went down to Louisiana, you let the Gulf of Mexico drop down by about 20 or 50 meters, you'd expose a bunch of channels in that delta that look just like this. And this tells us that the crater was once a lake basin with rivers flowing into it. But that's a hypothesis. We haven't proven anything, and so we have to figure out whether or not that occurred. But the important thing is, it tells you about a sedimentary record. And if we go back on Earth and we look at the records of life on early Earth, when did life originate on Earth? How do we know that? What's the oldest fossil on Earth? We see fossils of simple microorganisms in rocks that are about 3.5 billion years old, but they're always preserved in sedimentary rocks. So we had to first find these sedimentary rocks on Mars to know that that would give us hope that we might someday find something there. Okay, so you can go global with this. Instead of just looking at one little river system, let's look at the whole planet. So this is the whole planet. Take the sphere, lay it out flat, and this is what you get. And every place that you see yellow here is where there was a valley network cut into bedrock, and every place you see red is where there are major canyons cut into bedrock. And then, if you go back then over the last decade, and you compile the data of all the occurrences where the camera that's orbiting around Mars takes a picture of something that looks like a sedimentary rock, you find out that in the latitudinal belt, not too far south, not too far north, in this broad swath of latitude, we see evidence for erosion of the bedrock. And in the same broad swath, we see evidence for the deposition of sediment. This is a really good thing because it means it gives us lots of choices to go explore for it if we want to investigate the sedimentary rock record. Okay, a little bit more about the sedimentary rock record. So this is the wall of Valles Marineris, which is the biggest canyon in the solar system. The canyon is as long as the United States is wide, and it is much deeper than the Grand Canyon. This canyon is 5 miles deep, so it's 3,500 miles long and 5 miles deep. And in the walls, you can see layers of light material and dark material. And you can see the dark material kind of skidding down slope here, making these streaks that extend downward there. Okay, but it took a rover called Opportunity back in 2004 to land on Mars with the hypothesis that there could be sedimentary layers seen from orbit. The rover lands, we drive about 100 meters, and we find the wall of this crater with a beautiful sedimentary record in there. And you can see all kinds of interesting features. Some of them are geometric, and you can see the layers here are at a different angle than the layers down here, and the orientation of these layers down here tell us that these layers were once in place by ancient sand dunes migrating across the surface of Mars. But it tells us that in the sedimentary record, these records are the storehouse of information that tells us about the environmental evolution of a planet. Okay, then the plot thickened a little bit. There was another phase of orbiters that started going around the planet. They took the observations that we made locally and extended them globally. That's what the orbiters do. The landers and the rovers give you ground truth, and the orbiters allow you to extend your understanding to a much broader scale. So here is this great canyon of Mars called Valles Marineris, as long as the United States and 5 miles deep. This is a branch of the canyon. And then there's a basin over here. It's completely isolated except for these channels that run up to the north here. But interestingly, in that basin is a mountain. And we're going to zoom in and look at that mountain right there. And this is what you see, is that this mountain is made of layers. And now we're seeing mineralogy. So we don't just see the geometry of a layered deposit. Think of a bunch of pancakes stacked on top of each other. We can now tell whether or not the pancake has blueberries in it or chocolate chips. And so this stacking that you see down here, this is a mineral called magnesium sulfate. Its name is kieserite. And my grandmother used to dissolve it in water and soak her feet in it. People do it today. But there's another one called calcium sulfate, which is known as gypsum. And if you're familiar with construction, a lot of the walls and buildings are made of sheetrock. Well, the sheetrock is made out of gypsum. So this is really interesting because the sheetrock is derived from a deposit, and if you go look at the mine site, that tells us where seawater once dried up on Earth. So you take a bucket of seawater, you dry it up, what you're going to get mostly out of that water is salt that you sprinkle on your food, and then after that you're going to get calcium sulfate. So what we wonder is, maybe once in this basin, there was once water that dried up and left these minerals behind. Is that we can look down from orbit, and this is actually the data. This is a perspective view of the topography. And the red layer down here is this magnesium sulfate, and the blue on top is the calcium sulfate. And so the red corresponds to this stuff that's not so well layered, and the blue corresponds to stuff that's very well layered. That's a pretty primitive understanding of how to get a sense of the geological history of the planet, but it is exactly identical in time to where we were as humans working on Earth back in the middle 1800s. Actually, the end of the 1700s. This guy, William Smith, was a civil engineer working in England building canals. And as he made the canals, he looked at the geology and began to see pieces fall together. And what he noticed was that there is a pattern of rocks across England going from Wales over here in the west to the White Cliffs of Dover and then the English Channel over here. And these layers are basically all dipping in one direction. And they've got different names that he gave them, and they were very important to him because you could extract minerals and things like coal that the Industrial Revolution of England depended on. And one of them in particular, this green stuff over here, is called chalk. And the White Cliffs of Dover are white because they're made out of chalk. And if you get the Latin root for chalk, it's Creta. It also corresponds to a name in the rock record called the Cretaceous, that many of you will know as the time of dinosaurs. So it actually turns out in the history of understanding the Earth, there are rock units that are known because of their minerals. So early on in the history of understanding the geology of Earth, we were interested not only in the layers, but the minerals that were in these layers. Okay. Now, this is a sacred place in understanding the history of the Earth. If you go, it's called Sicker Point, and if you go to northeastern Scotland, you can go see it there. And it was observed by James Hutton and his colleague John Playfair back in 1815, at a time when understanding of the Earth was governed more by a biblical record of what the sequence of events were. And these guys looked at these rock layers and realized that these ones are dipping vertically, but they must once have been horizontal. And so they got tipped up on end, eroded, and then other layers were deposited on top of them across what's called an unconformity. And then after that, the layers were tipped again. But the important part here is that these guys recognized that in order to take these rocks and tip them, they must have made mountains. And so they had a hypothesis that once there was a flat sea, that then got converted into a mountain range, and then got eroded down. And this must have taken eons of time. And so out of this comes this famous phrase, the mind seemed to grow giddy looking so back into the abyss of time. And what these scientists were doing was recognizing that the age of the Earth was much greater than you could possibly imagine. And after that, after the discovery of radioactivity, it was eventually proven. But that realization is kind of where we are on Mars now. And so here's a book that you can read if you're interested in, Map That Changed the World. It talks all about this discovery and this phase of enlightenment and the application of geology to understanding the antiquity of the Earth. And this is Smith's map, and the point of this map was for it to be applied for the derivation of resources to help fuel the Industrial Revolution. Okay, now one interesting thing that comes out of this is the notion of correlation. And so these are two canals that he would have created, and what he noted was that there are some kinds of rocks that have this brick pattern, and over here they have one kind of fossil in it called brachiopod, and over here they have another kind of fossil in it called ammonite. And what you realized was that in order to correlate the rock layers one to the other, you needed an independent measure of the passage of time. And on Earth, that passage of time is measured by biological evolution. So all these fossils change systematically, always in the same direction, but the rock layers, the composition comes and goes. Now, that insight resulted in a simple time scale where you took known geological history and you came up with some periods called Paleozoic, Mesozoic, Cenozoic. And so in the beginning, back in the 1860s, we have fossils. We don't do that on Mars, so what we do is we take minerals and elements and their isotopes and we determine their age, and that's how we can do correlation on Mars. Okay, so what does all this mean for Mars? So the era that we live in now means that you can fly an orbiter around Mars and map the surface and look for the minerals, and they basically fit into three groups. And these columns that geologists like to draw have older at the bottom, younger at the top. Don't try to read any of the words here, it's way too complicated. Just look at the colors. And what you're supposed to recognize is that what's down at the bottom is mostly green, what's in the middle is mostly yellow and red, and what's at the top is mostly brown. And that corresponds to a history, a planetary history, where the planet once made clays, that's what the green represents here, and then it transitioned into a planet that made these sulfate minerals, that my grandmother feeding. And then we have the top up here, which is brown, that's iron oxide, with no water in it at all. The key is that this mineral down here, clay minerals, all clay minerals have water in their structure. And these sulfate minerals have water in their structure. But then something catastrophic happened and the planet dried out. I like to call it the Great Desiccation event. At about the same time in history when Earth was going off and becoming green due to the evolution of oxygen and photosynthesis and putting a lot of oxygen in the atmosphere that eventually made it possible for animals to evolve, Mars was drying up and dying. And so this Great Desiccation event is then represented by this transition from green to yellow and red to brown. And it's not a happy story. It would have been cool if Mars would have gone on to do its own greening, but it didn't. And so what we'd like to do is stick down here in the older part of the record when we know on Earth life seemed to emerge and originate, and ask the question, can you find evidence for past materials made by microorganisms like organic compounds? That's our mission. That's what we're about, and we went to a place called Gale Crater, and that's the mountain. And what you see in that mountain is a history where you go from green layers down to the bottom, through the sulfates, clays, sulfates, anhydrous iron oxides. Okay, so let's talk a little bit about that landing study. Here is now a different type of representation of Gale Crater from orbit based on laser ranging data. So we have a laser that flies around and it zaps down and it measures the topography of everything. Here's the mountain in the middle that we saw early on. On the north side of that, there's a depression. And here's a scale for color. So white is the lowest thing on this map. The hotter colors are high. There's a topographic gradient running from south to north. The crater hit right on the margin of a big escarpment that goes all the way around Mars. But notice that the basin here has the lowest depressions, even lower than what are called the northern plains out here. There's one other crater that kind of smacked down in there and made a depression which is as deep as the floor of Gale Crater is. But that was attractive to us as a team, because we'd like to find a place where water is gathered. And you know, I listened to all these complicated arguments, all sophisticated science. At the end of the day, when I went home and I thought about the different places we were going, the one I liked the best was I could look at this map and see rivers cut into the bedrock, and over here, these rivers were flowing right into the crater. So the simplest argument at the best, at the end of the day, was the most elegant one that I was also able to sell to NASA headquarters. Okay, why did this mountain form? This is another big mystery. It's totally independent of the water, and this is the business about peering back into the abyss of time. What we recognize is that there's a family of craters on Mars, of which Gale is actually an end member, with its mountain in the middle. But what we can see at the other extreme is that there are big craters. These craters are all 150 kilometers in diameter, so they're the size of the LA basin. When you look at one of these pictures and you imagine how big this is, Imagine going from the San Gabriel Mountains up here, down through Anaheim, past Angel Stadium, and then at some point you wind up down here at Fort Pendleton. It's about that scale. That's how big that is. It'll take you 2 hours to drive across there. And what's happening is that these craters have all been filled up after something smacked into the surface of Mars and made a bowl. It then filled it up. And then the bowl is basically being exhumed so that it looks like a donut with a moat coming around here. And then in the extreme case, we probably get gale that squeeze this mountain behind. So if you're wondering where that mountain comes from, that's how we think these mountains form on Mars. Probably by billions of years of the wind blowing around in a circular pattern and eroding the rock away. It's a very un-Earth-like process. On Earth it rains a lot. Most of the erosion occurs by rainfall. On Mars we think it's caused by the wind blowing sand grains and abrading it away. Okay, here's where we landed. This landing ellipse is 20 kilometers long. We found the flattest place that we could land the vehicle, and to our great surprise, that flattest place was also where the lowest point was, which is just where we wanted to be to find evidence if there was water that once pooled there. And we're interested again in this stratigraphy for the same reason that if you've ever been to the Grand Canyon and you look down in there, these layers represent the history of the Earth. And what geologists do that go back and study the history of the Earth is to read this like a book. And the layers that are down at the bottom are the first chapters, and the layers that are up at the top are the later chapters, and in between we turn the pages and we read the rock record to tell us what was happening on Earth. Now on Earth, it's a story about the evolution of life, and you go through all these rock layers, and you go from trilobites down here, and up here you've got dinosaurs. And that's kind of cool. And on Mars, we of course love to do that, but we'd like to first find anything at all. Okay, and to give you a sense of the scale of Gale Crater, here's the Grand Canyon. It's about a mile deep, and Gale is about 3 miles high in comparison. So it's actually a much longer record than what we would see in the Grand Canyon. Here it is a little bit closer up. Let's fly into the place. Curiosity is now right down here, having driven 8 kilometers away from the landing ellipse. And we're going to be working our way up as the years go by through these different layers that you see here. Going from where the clays are into where the sulfates are, and then eventually up here we go through what we call cemented fractures. That means more water, and after that it gets dry. Okay, what about the vehicle itself? So here's an image of Curiosity, our Curiosity's twin sister that we keep at JPL to do experiments with. Curiosity is the size of a car. Earlier on, a decade ago, we had Spirit Opportunity the size of a golf cart, and then a decade before that, back in the 90s, we had Sojourner Truth, who was the rover that was deployed from the Pathfinder lander that explored the surface of Mars and demonstrated that we had the right technology to get the job done. As a technology demonstration, what we were doing was testing out this 6-wheel drive rocker bogie suspension, which allows the vehicle, which is solar powered, to keep its solar panel flat as we drive over rocks as high as the diameter of the wheel. So all those motions are absorbed by this rocker bogie suspension. The solar panel, the biggest threat that we had was that maybe if you land a solar panel on Mars, we know we have these global encircling dust storms. The dust is going to settle down on the panel, and maybe you're going to die to a lack of energy. So we would measure the dust accretion rates with these solar panels. They both worked. We scaled it up, and in the next decade we went ahead with a rover whose goal was to find evidence of water on the surface of Mars in ancient rocks. That worked. We go ahead to the next decade, and now we get Curiosity with a mobile chemistry laboratory to try to characterize the composition of the water and also to look for organic compounds. And you can see the heritage coming through here with the same 6-wheel drive rocker bogie suspension, a big arm that sticks out in front. Opportunity had a smaller arm. The big change is that what you don't see are the solar panels anymore, because this is a nuclear-powered rover, because we want to operate Curiosity at night, and that turns out to be a more reliable power source than solar. Sun goes down, you don't get so much energy with solar. Here's Curiosity right before we shipped her off. It's still one of my favorite pictures of the whole mission. The vehicle is 2 meters long. When the mast stands up, it is also 2 meters high. When you extend the arm out in front, You could reach the arm up with the height of the rover and dunk a basketball. So it's about 10 feet, just from the front of the rover, not to mention what's behind here. That's a lot of metal. And so what's going on here is that on the surface of Mars, it's a harsh environment. The daytime high is about 0 degrees centigrade. The nighttime low is minus 100 degrees. So every day on Mars, as the sun rises and sets, the temperature on the surface of Mars changes by 100 degrees. And all this metal expands and contracts. And that creates problems for us because it's a lot of wiring in there, and all that wire is expanding and contracting. And the vehicle, if we are drilling a hole and we get stuck and the sun goes down, suddenly the vehicle's going to want to shrink and you're yanking against the drill bit. That's not good either. So we need to know exactly how this vehicle is going to perform under the thermal stress. So this engineer, who's in a white suit, because she doesn't want to create a thermal pollution environment within this test bed, is taking this sensor and touching the tip of the rover as the rover gets illuminated with a light source that has the same intensity that the sun does on Mars. And so our models make a prediction of what the temperature should be of the metal at the surface of the rover, and then we collect data to see how well our models actually work. And then we change things around until we can do a better job of predicting the temperature. Okay. Eventually, we're done all the testing, and we ship Curiosity off to Cape Canaveral. She gets integrated into an Atlas 541 rocket right up here, approximately behind the flag. And if you ever wondered how NASA gets all these launches done all the time, it's because we've cut a deal with Russia and bought all their ICBM nuclear rocket boosters, and they get shipped over to the U.S., and these solid rocket boosters on here all have Cyrillic lettering on them. And it works great. So that's a way that we convert war into peace and use it for science missions. Okay. I think people have seen the 7 minutes of terror video. Okay, just a few. I'm going to show you a hybrid version of that in a minute, but here's what to look out for. So here's the problem. We launch the vehicle, it takes off, it leaves Earth's atmosphere, influence of its gravitational field, spends 8 months in space in the cruise phase until it arrives at Mars, and when it does, it's roughly going, I'm going to round all these off for you here, it's roughly going 10,000 miles an hour. That's too fast to land safely on the ground. So what you do is, you enter the atmosphere, the vehicle has a heat shield, the friction in the atmosphere causes the dissipation of energy, and then from that we slow down to about 1,000 miles an hour, and then we deploy a parachute which slows it down to about 100 miles an hour, and then after that we do this really crazy thing that was never done before on any planet, where the heat shield falls away and a separate vehicle comes out on its own and starts flying around under rocket-controlled propulsion system. And then in the last phases of landing, this vehicle hovers above the surface of the ground and reels the rover out on a set of cables until it touches the ground at about 1 to 10 miles an hour, depending on how well the thing was calculated where it's landing. And then the cables are cut, this vehicle flies away and crashes, and the rover is pretty much born good to go. And so what we do is, that's the way that you manage 1 ton of mass, trying to get it on the surface of Mars. Okay, so I can't remember if this is coming up next, but if I do hit the video next, here's what to watch out for. You're going to see a bunch of people reacting in real time to the events that are happening on Mars. So people like you guys are watching a screen, and what they're seeing is the data being returned to Earth and indicates that a series of events went right. We reached the top of the atmosphere. We deployed the parachute. You'll see the heat shield fall away at one point. Then the vehicle's out flying around on its own, and then eventually there's touchdown, cable cut, and then after that you'll see everybody really jumping up and down here.
They're looking good. Vehicle reports entering a base. At this time, we'll begin pressurizing the propulsion system to increase the thrust of the system. So use that for all the maneuvering in the atmosphere we're about to do. We're standing by for guided start of guided entry. be able to feel the atmosphere as we go in here. The vehicle just reported via tones that it has started guided entry. At this time, the vehicle was beginning to steer its way to the target. We have seen peak acceleration. Starting its first angle. Just reporting that we are seeing G's on the order of 11 to 12 feet. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Seat shields have separated. We're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers per second. Standing by for backshell separation. We are in power flight. We're at an altitude of 1 kilometer per second. Standing by for sky training. Sky training started. Stay alive, you remain strong. Touchdown confirmed. We're seeing one line.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
So we made it. You know, at that point in the mission, all of us in the blue shirts, some of them went back to their day jobs at Best Buy, and the rest of us then go on to do science. And if you're one of those engineers, it's such a decisive moment in your life because everything that you've been working on for a decade comes to a very definitive end. Science, you begin this very nebulous journey with what's going to happen. You know, well, this landing was great. You know, will it work out? Will we discover anything? And so you land, and you have this very mixed feeling about whether or not this is ever going to be worth anything. So what I'm going to do now is show you what we found. It turned out that you know, we found some pretty good stuff right out of the chutes based on some mapping that we had done, and I'll try to hit the highlights. So this was an amazing picture for a couple of reasons. One is it's startling because you actually get to see topography and landscapes on Mars much closer than any mission before because our landing system, that sky crane allowed us to fly out of all kinds of errors to allow in a much smaller area, which means we could fly into the valley in between mountains. What we hadn't appreciated is that the rim of the crater is also an awe-inspiring bit of topography. We had been focused on the central mountain, and we had more or less ignored the rim. And so what you see then here is topographic mountain, valleys coming down in it where you can see evidence where there was once rivers, and then out in front of it, rock layers of the type that we're looking for. So we realized immediately that this was a very good scenario. But it also made us feel like we were at home. If you've ever driven to LA to Vegas and you look up at the valleys, you know, it looks very similar to what you see in the basin range topography on the way to Vegas, little LA smog coming in here. Turns out everything here that you see is dust. And actually most of what you see on your way to Vegas is also dust. It's not just LA pollution. And, but you know, it kind of made us feel like home. We liked this area right off the bat. It just didn't seem so foreign. And that's a big change in the mindset of planetary exploration. And I like to compare it to the transition from the Star Trek mode to Sherlock Holmes mode. And science has two ways that it does investigation. And one is inductive, which is you observe and seek to explain. You've got no clue what's there. Let's build something. Let's go look at it. Let's make a telescope and stare at the moon. And then from that, you generate hypotheses and understanding, which leads eventually to a more mature phase of science, which is more deductive, where you make a prediction and then seek to observe it. And that's the phase that we're in right now on Mars. We really don't want freaky, weird places because we'd like to use our human experience to be able to explore a very foreign place. And the more those foreign lands look like home, the more our experience applies. So this was really reassuring that we were on the right track. But as cool as that was, this is still my favorite picture of the entire mission. When we turned the rover around and aimed the cameras at the mountain, this is what we saw. This is only the lower foothills of the mountain. The rest of it's up over here somewhere. But this is the part where, from orbit, we saw the evidence that the layers that you see here were made out of these minerals that have water in their structure. If we can just traverse our way over there and trundle up these hills, we're going to get some insight into the early evolution of the planet. So that was our goal. And for scale, this one is about 50 meters high. This one would be probably about as tall as this building is that we're in right now. So this terrain is going to be cool when we start driving around it one day. It's going to be like walking around the campus here with a bunch of hills that make you feel a little cozy. You know, not completely out on a wind-swept rocky plain, which is what all previous views of Mars have looked like. Again, the credit goes to the landing system for getting us into this geologically interesting environment. We made a map looking down from orbit, and we saw the rivers that we thought were flowing once upon a time from the crater rim. Here's the mountain over here. And we have these things called an alluvial fan. Some of you may know what they are. If you go on your way to Vegas, if you turn left at Baker and drive north, you're going to see huge alluvial fans coming out of these mountains. It gets wet up in the mountains, the water flows downhill, the flow spreads out, and it leaves a sedimentary deposit along. So we thought that was good. It turns out where we landed was right here. And for a geologist, you're always looking to double up on a unit. If you land right in the middle of this, you're like, well, we're going to study that, but we're going to have to drive a long way to try to find something new. What happened to us is that we landed right here on the green stuff. And then it turned out we were adjacent to the brown stuff and also the red stuff. It's what we call a triple junction. So if we can just drive 500 meters in the wrong direction, we might be able to get a threefer over here. And so what we had to do was I get on an airplane, fly back to NASA headquarters, and explain to headquarters why we want to drive in the opposite direction from this mountain that we've been pounding our fist about for the last 4 years. Okay, we got permission to do it. It is a team and off we went. What you can see over here is what looks like a little butterfly. This is a picture from orbit. Curiosity is in the middle. She has a white deck, and so there's a lot of solar reflection off of that. And then to the left and right, up and down, you can see where the rocket thrusters blew holes in the ground and blew all the dust away and all the rock, all the loose soil away. The area that looks dark here is because this is a false color image, it's not true color. So here the dark area is where the rocket thrusters, their momentum spread out laterally and blew the dust away over a broader area, but without scouring down the rock. And so when we looked at this, we thought, gosh, you know, we just have to go to this triple junction area. And here are the three terrain types. You don't have to be a geologist to get this. You look at this one, you see kind of low rolling hills, looks sort of hummocky. We call it the hummocky terrain. You look over this one here, it's got all these craters pockmarked all over the landscape here. It looks like the moon. We call it the crater terrain. And then you see this one over here, it's light tone. You can see fractures running across it. We call it the light tone fracture terrain. And what we did was we drove down into this embayment that you can see here. Here's a little cliff. It's about 2 meters high. And we wanted to get down in there where all these things came together. We called it Yellowknife Bay. So we drove across here a distance of about 5 football fields to get there. And then this is where we hit pay dirt. When we got there, we stopped and we took pictures down into the area where we had driven to. It took us many months to get there. Because you don't just go off to the races. You want to make sure that all the rover, all its capabilities are working properly, and you don't get yourself in trouble just by dashing off. So it took us about 4 months to get there. And this is the last of the gravel that you see of the so-called hummocky terrain. And now what you see out in front of you in the light tone fractured terrain is a new kind of a landscape that kind of reminds me of Moab, Utah. Looks like the kind of place you want to get your mountain bike out and drive around down in here. And so we drove the rover around what we call the diving platforms, down into the valley, came over about here, and right about there is where we stopped and realized this is where we actually need to drill a hole. Here's the rock that we drilled into. Probably not many folks have been to a mining area, but if you're a geologist, one of the old guys digging around with a rock hammer back in the 1800s in the Sierra Nevada looking for a mine, what you're really looking for is not just rock, you're looking for fractured rock. And you're looking for fractured rock filled in with veins. So these are veins running through. What the veins tell you is that there's fluid moving through there. On Earth, we're looking for gold and silver. That's what the old-time prospectors were doing. What we want to do is we're looking for the veins because they tell us water must flow through this rock, and we're after the water, because if we don't find the water, we can't do all the experiments that we're doing. Again, by water, I mean water that's bound into a mineral. It's not like free-flowing on the surface today. So we saw this, and all these bumps and knobs that you see sticking up here, those again represent chemical reactions that happen in the rock that it all looked good to us. So here we go. This is what you get for $2.5 billion of taxpayer money. Pinnacle of human achievement, 7 minutes of terror, sky crane coming down, driving. You know, those EEL guys had their 7 minutes of terror. I like to say that we had our 7 months of terror. Because you don't know that you're going to find something good. Everybody, newspaper, media, they're constantly writing, they're calling, wanting to know if you guys found anything yet. And so here we go. We drill the hole. What's cool about it is that the rock looks great. I'll come back to that in a minute. And then you see the fractures that you saw from the surface. They do extend down into the rock. That's reassuring to know. And then we've got a laser on this rover that can shoot out about 10 feet out in front of us. So after we drilled the hole, we decided to shoot at it, and here is an array of 10 shot points going up the side here, and they give us a sense right off the bat about what the chemical composition is, and then we can begin to fine-tune our other instruments in anticipation of getting this rock powdered and processing it, and then dumping it into the instruments that we have on the rover that are very much like the ones we have on Earth. Let me take you through one of them. And describe to you how we analyze a rock powder on Earth. So this is an instrument called SAM. It stands for Sample Analysis of Mars. It's got 2 spectrometers. You don't even have to know what this means, I'll explain it to you. But it measures the abundance of elements and the mass of elements. The mass of elements tells us how we can differentiate calcium from carbon, for example. We're interested in carbon because it's the building block of all organic molecules, including us. And so what we do is we take the drilled rock sample. The powder gets dumped into the sample manipulation system, which is actually just a little cup. It's about the diameter of a piece of chalk. It's hollow in the middle. We dump it into that sample holder. And then that sample holder goes into an oven. So this carousel rotates around. The sample's dumped into the cup. The cup gets put into the oven, and we heat it up. And so what we're doing is we're burning rocks. And the way it works is it's like baking a cake. You go home, you open the door, somebody's in the kitchen cooking. Immediately you can smell that there's a cake in the oven. You know that smell, you know it's going to be good. And the reason you smell it, the other thing you might notice is sometimes you walk in that room and it just feels like it's humid. It's kind of moist in there. And so what's happening is the cake is heating up, and the water that was once a liquid is now turning into a gas, and it's going into the atmosphere. And you detect it, your chemical sensor detects it. And then the sugar that you put in the cake, looking for the molecules that have carbon in them. And we analyze them with this instrument down here, and that tells us whether or not there could be organic molecules in these ancient rocks on Mars. So here's what it looks like when we look at a big cake, a burned rock on Mars. This axis here, the higher it gets on this axis, the more of the stuff there is. Over here is temperature, so we're heating it up. We've long since burned an actual cake. 250 centigrade is way too hot for an oven. And we're going up to 800 degrees. If we go up to 1,000 degrees, many rocks start to actually melt. We don't want that to happen because that's going to gunk our system up. We just want to burn them and get all their gases out. So what you're seeing here, as the temperature increases, look at the blue line. This is oxygen. Oxygen comes off. It peaks and then it goes down again. No more oxygen. Then we see carbon dioxide coming off. It comes up and then it goes down again. No more carbon dioxide. Water is real interesting. Here's water coming off. We get a lot of water coming off. It starts to go down, but then it comes back again. And then after that it goes down, comes up again one last time, and comes down. That water that's coming off here at about 700 degrees centigrade, that's the water that's bound into the minerals. And so we collect that water that comes out of the minerals, and then we can measure all kinds of stuff about it that I won't go into, but that tells us once that this is a good place for life to have been. And the sulfur that you see down here, you add it up, and the carbon dioxide, basically everything that you see in this picture is our home run on Mars, but the reason we built the rover to drill that hole and analyze it is all good. Okay. A little bit about the mineralogy, and again, I'm going to try to keep this as simple as possible. Here's a list of names, don't worry about it. Over here, this name Rock Nest, that's a pile of sand on the surface of Mars that we reached out, grabbed a scoop of the sand, chucked it into the chemistry laboratory and analyzed it, and this is what we got. And then here's the hole where we drilled, named after a guy called John Klein. The important thing to notice here is that there's a mineral called olivine, and there's a lot of it in the sand that's blown around on Mars, but in the ancient rock, it drops, its abundance drops way down. And then there's a mineral down here called smectite. That's a clay mineral. And what's happening is that there's none of it in the sand on Mars, but in the rock on Mars, there's 20 to 30% of it. That's the big discovery for us mineralogically. And seeing this chemical transformation, this mineralogical transformation, if you're a microorganism, most people are used to thinking about photosynthesis. There's CO2 in the atmosphere. A plant takes the CO2 in the presence of sunlight, converts it into organic compounds. It builds itself. And then it gives off oxygen as a byproduct. There's another group of organisms that just live on chemical energy. They literally feed off of rocks. And the list of materials that you see over in this column here is what tells us that we could have taken one of these microorganisms that lives on Earth in those kinds of environments, dropped it into this ancient wet place on Mars, and it would have been able to live and reproduce, and that's a good thing. It doesn't tell us if life ever originated on Mars, but it tells us as we go forward into the next decade that we should keep doing this because so far there's not any bummers that we've seen here. Okay, the business about color is the simplest way to tie up all the science that we've done. A decade ago, when Opportunity landed on the surface of Mars, we drove around, and we didn't have a drill, but we had a scraper. It was a more primitive device. We weren't ready to build a drill yet. And when we scraped it on the surface of the rock, it turned out to be red. The rock turned out to be red stuff, just like the planet, the red planet is red today. The reason they're both red is it's a mineral called hematite, and it's iron oxide, but there's no water in there. So this is not really a good scenario for habitability. And when you drill into the rock that we drilled, here's red Mars on the surface of today, which is a lifeless planet today. You go back into this ancient rock, and unlike what you had here, the drill tailings are gray. And what that tells you is that the rock had the chemical energy and the wetness to support life if it had originated on Mars. And these are just samples on Earth. Maybe you've seen some of these things. If you look at brownstone buildings on the East Coast, Washington, D.C., Philadelphia, New York City, Boston, They all come from red rocks, which are not really well known for containing a lot of organic matter, but the gray rocks are what oil companies are out looking for. In the LA basin here, you find a lot of gray rocks that would have produced organic matter. So we think we're on the right track. Okay, and 10 years ago, the story we would have told you, if there would have been a scenario to keep life alive on Mars, we would have gone to a place in Spain called Rio Tinto, and the river is red because iron is dissolved in the water. And I won't get into chemistry other than tell you that, and under oxidizing conditions where we live, iron doesn't easily go into solution in water. But here, iron goes from the +2 state to the +3 state and is soluble in water and keeps it red because the pH is so low. This is like pH 1. This is so acidic that if you stick your finger in the water, for more than an hour, it's going to start to dissolve. And yet, there are some kinds of microorganisms called acidophiles that can live there, but they are on the hairy edge of existence. So you could potentially argue that Mars is a habitable environment, but just barely. Okay, instead, what we have now, based on what Curiosity found, is more like what you get if you go to South Australia. There's a lot of the kind of rocks that we find on Mars, and the water comes and goes. This is the Southern Ocean out here. But these are lakes that form when it rains, and the groundwater percolates through the hillsides. And then for a while, these lakes are wet, but then they dry up. But even when they're dry, if you dig down with a shovel in here, it gets kind of mucky down in there. And all the chemical and mineralogical ingredients that you have here today are supporting life. Very abundant, prolific life. And these are the things that we found at Gale Crater. So again, we did not find evidence for life. We didn't prove if life ever originated on Mars, but what we have done is show that Mars had the right environmental conditions to support life, and quite generously so if it had ever originated. One last analogy for you. A battery is a little chemical system. Think of it as a rock. It's solid, you know it's heavy, if you throw it at somebody it's going to hurt. It has a positive end and a negative end. If you hook up a wire and put a light bulb in the middle, you get a flow of energy. These microbes do the same thing. They use rocks like little chemical batteries, and there's a flow of electrons that causes them to be able to live. But the problem is that the reason that honey does not spoil on your shelf is because there's water there, but there's not enough of it. So here's a place on Earth, woohoo, we found water on Earth. The problem is this is not a habitable environment because it's too salty, so to speak, even though it's sugar, think of it as a salt. There's just not enough water in there, so if a microbe falls in there, it's going to die and the honey won't spoil. So the problem with that previous place that we found on Mars is not only is it very acidic, it also would have reconstructed to have been very, very salty. So salty that we don't think it could have supported life. So again, what we found at Gale Crater is a freshwater lake. As I said in the media, if we had been at that lake 3.8 billion years ago, you could have drank a glass full of it. It would have been just fine. Okay, so here's where we're going. We have just arrived last month. We finally got to the foothills. We're right down in here, and we're beginning our exploration. And what I wanted to do is just finish up with one last fun thing. So we got a flat tire on Mars. It seems like every mission of exploration at some point runs into trouble, and we had our fair share of trouble. I think we're out of the woods, but it's a study in progress. So we went from our glorious moment. If you're a scientist, the best thing that can ever happen is to get some papers published in Science magazine. The even better thing is you make the cover of the Rolling Stone. We got really excited about this. In December of last year, I was up in San Francisco. We had our press briefing. We gave a bunch of papers to a professional conference. Literally the next day, I get a call from the project manager, John, you got to come home, you've got a problem. And here's the problem. We have wheels. They're made out of metal. They're thin metal because we don't want a lot of weight when we're landing. That's tough to manage for the landing system. A sol is a day on Mars. After 400 days, we took a picture. We expected to get some dents and dings. But, you know, it turned out to be the kind of thing where we began to worry, you know, how bad could this actually get? So we decided about 2 months later to take another set of images, and now for the first time we actually saw a puncture. That's not just a divot there, there's a crack at the bottom of that divot, and that didn't look real good. So then, the next thing that happened was we decided to aim the cameras. We take the arm out, we reach back and aim at the wheels. And what you can see going on here is that these are holes that were built in the wheel, so when the wheel rolls, there's three rows of holes in here, and they spell JPL in Morse code. It's kind of a fun, geeky thing to do. But what's not good is when you look at the front of the wheel where there's supposed to be metal, and you can see the planet on the other side of the metal wheel. That's not good. So we realized that these wheels were getting punctured, there were holes in them. Here's another crack and fracture that you see here, and we are literally dying with 1,000 cuts. So what do you do about this? Well, this is where we discovered it. We had to go all the way down here to make it to the mountain. This is where we had our big jumping up and down, happy moment with signs, covers, and all that stuff. Then we drove along, and right about here is when I got the phone call that I needed to come home. And after that time, we really slowed down. So what do you do about this? So I'm the lead scientist, and my colleague is the lead engineer. We divided the team up into 2 task forces. And we had to come up with a way to solve this problem. And it's a classic NASA moment. Because there's no AAA on Mars. It's like somebody shows up and over and gives us some wheels. So scientists are great the way that they work. This is where we came to a grinding halt. And the question is, how do we avoid all these rocks that are killing us? You know, we got to do something. So what I did was send a bunch of people off into a weekend retreat to come up with some ideas to suggest what to do. And there were 1, 2, 3, 4, 5, 6, 7 people that went into that room. Yeah. And nobody agreed on anything. We had 7 different groups, 7 different scientists, 7 different routes. But the reason this happened is we had no hypothesis. We didn't know it was hurting the wheels. So almost anything goes. So this route that's advocated down here is the straightest route to get between this point and that point where we want to be going. All paths had to lead to this point because this is where one of our next drill sites was supposed to be. So one route, just take the shortest route. Damage is proportional to drive distance. Just drive less and you'll be better off. Then you had another route which sort of optimized and squiggled its way along the highest part. That's the high road route. And then you have this one over here, which is the low road. You take the high road, I'll take the low, literally. That was the argument. And this route, the argument was, well, the sand and grit and stuff is going to blow off the high points and go down into the valley, and maybe we'll get a smoother ride down there. The problem with this route was that it was also the longest route. And this route was a hybrid of both. Take a longer route, but stay high, go high, get low, then stay low for the very end all the way down to here. And every combination of this. In the end, we picked this route, and it turned out to be a game changer for the mission. But it was a really hard sell, because in my interactions with the lead engineer, you know, they're not geologists. And it's kind of hard to accept a perfectly good argument that the safest route is the shortest route. And now you're recommending the longest route. But John, what if you guys are wrong? What if you don't know what you're doing? And so we're looking down from the pictures from orbit, and you can kind of see down in here that there are valleys, and they look kind of smooth. So we were hoping that the sand would be down in there. So we did some mapping. Geologists always do mapping, and we broke it down into terrain types, and we considered the red to be the worst, then orange, then yellow, then blue, and green to be the best. So here's the long route. But the hard part with the long route, there's a couple of narrow gaps where you have to go through passes in order to make it safely to the end point down here. But for the most part, with the exception of those few passes that you have to drive up and through, it looks like a pretty darn good route. So we decided to go with it. Okay, so we turned right, hard right, and we had to go through a place called Dingo Gap. But it turned out, in order to get down into this valley that's on the other side of the gap, it turns out there was a big sand dune in the way there. Of all the things that you can imagine to build more tension, the whole mission is worried about more wheel damage. And now we're suggesting to get to the promised land, we've got to go up and over the biggest sand dune that's ever been seen on Mars that a rover hasn't driven on. And, you know, what could go wrong? So we got up there, we tiptoed our way up there. We had the 2 front wheels on the top of the sand dune and the 2 rear wheels still on bedrock. So that way, then we perched and we sat there and we waited for the sand dune to compact to find out how squishy it was. The more squishy it is, the less we like it, the more firm it is, the more we're going to hit the gas pedal the next day and go over. The important thing is that we do see down here in what we call Moonlight Valley, the River of Hope. This is a low point, and you can see lots of sand and gravel down in there, and even some little small sand dunes here. The hard part is that in order to get through Dingo Gap, on the other side of the sand dune is an avalanche deposit of a bunch of rocks that slip down here. So as we're driving across this, if the vehicle careens to the right, we can then collide with a bunch of rocks here. That's not good either. So it was a very tense moment. We eventually collected the data that we thought was important, and down we went. We stopped, we turned around, and we looked back at our path. So here we are, coming back over the top of the dune. There was an inversion maneuver that was programmed into the robot to make sure that we did not slide down into these rocks. So here, we stop the vehicle, do a wheel wiggle, check our traction, and then have the vehicle skitch a little bit to the right and then head across the hill over here. So a successful drive in the bag, and off we went. Worked out well. We think we've got a handle on the problem now, and this is where we were going. And so what you can see here is our path now coming down through the long low road, and where you see the tracks on the surface of Mars, this is a satellite orbiter that's 25 miles up, going around Mars, taking a picture of our rover. And the tracks here for scale, they're about 1.5 meters apart. And as we go along, we draw a straight segment, we do a turn in place. It is a donut because it is a donut. And then we go to here, we do it again, and then we approach the rock. The reason we did this one here is because we do want to approach this rock, but we don't want to slide into it. So by doing these turns, it tells us what the terrain properties are like. And then after that, we study the rock, come around the corner, drive over this way, and eventually work our way down here, and there you see Curiosity. So she's 2 meters long. And then this little knob that you see sticking out here is this one. So this is Curiosity's picture of the same outcrop. And that's the one that we then went up to and eventually were able to drill, having made it with a minimal amount of wheel wear. So that's it. That's the story. We have now driven on past that outcrop. We've just arrived down in here at the base of Mount Sharp, and so for the next couple of years, we're going to be working our way steadily. So thanks for listening.